Imagine a single application split into 100 containers. 100 small machines, each with a job, each able to fail in its own quiet way. A health check missed, a node that simply vanishes, a traffic spike that turns a calm afternoon into a stampede. Before orchestration, someone had to watch that fleet by hand, restart what died, copy updates one box at a time, guess where the next request should land. This is the crisis Docker Swarm was built to answer. Not a prettier terminal, a question of survival. Who keeps a crowded fleet of containers alive when machines fail and demand suddenly surges? Docker Swarm is a container orchestration engine. In plain language, it is software that treats many containers as one service, and then fights to keep that service looking the way you said it should look. It was included in Docker's own container runtime in June of 2016. It also lives in Mirantis Container Runtime, sometimes called MCR, which takes a Docker engine and adds enterprise features, including security hardening. The important part is not the brand history, it is the promise. You already have Docker, and Swarm is waiting inside it. You do not download a second universe. You turn a mode on, and many hosts begin to act like one cluster. Why do we need it at all? Take that application of 100 containers again. You are no longer managing one process. You are managing a crowd that must behave as a single service. That act, managing and controlling multiple containers as one service, is orchestration. Swarm exists for the work that used to live in runbooks and night shift panic. Health checks on every container, making sure containers stay up on every system that should host them, scaling them up when the crowd arrives and down when the room empties, pushing the same update across the fleet, deploying a fixed set of containers so yesterday's accident does not become tomorrow's architecture, performing a rolling update so the show never fully stops, and load balancing so traffic does not crush one lucky container while its siblings sit idle. Each of those jobs is a different way the same question returns. Who is allowed to decide and who merely executes? The market already had other orchestrators. Kubernetes, Apache Mesos. Kubernetes was even more popular. So why turn Swarm on? Because Swarm schedules containers. It sets up networking predictions. It watches container health. It restarts anything that has died or anything judged unhealthy. And here is the part that matters when a whole machine disappears. If an entire node goes down, Swarm will reschedule those workloads on a different node. That is the difference between a container that dies and an application that dies. The first is a fact of life. The second is a failure of memory. Swarm's job is to remember the desired world and to keep shoving reality back toward it. There is a quieter reason people reach for Swarm. You do not have to download and install a separate software package just to orchestrate. It is already installed with Docker. All you need to do is turn Swarm mode on. That sounds like a convenience. In a documentary about infrastructure, convenience is often the whole plot. Teams delay orchestration because the next tool looks like a second career. Swarm's opening move is almost rude in its simplicity. You already paid the cognitive tax of Docker. Now the cluster is a switch, not a pilgrimage. The hook, of course, is whether a switch can still be enough when the fleet grows teeth. Swarm works with both Linux and Windows worker nodes. It can be extended with networking plugins, storage plugins, logging plugins. What it actually solves, though, is more intimate than a plugin catalog. It lets you declare your state instead of doing everything by hand. Resources, services, labels, constraints, written down in a YAML file. Declaration is a kind of memory you can version. Manual clicks are a kind of memory that leaves with the person who clicked. Once the desired world is written, Swarm can provision and decide where containers land. If you have several nodes, it will try to balance workloads across the cluster. That is high availability in the small. Not a slogan, just the refusal to pile every box on the same tired host. If traffic peaks and the web tier must grow, Swarm mode is where you ask for more. If a node runs out of resources or the whole node goes down, that is when the scheduler acts. Swarm also load balances traffic across multiple containers, tracks their health, and can expose services through an ingress path. The cluster is no longer a pile of terminals. It is a declared city with a traffic department. Before the architecture hardens into boxes, linger on the edges. Swarm works with Linux workers and Windows workers. That single sentence widens the city. The same desired state can, in principle, schedule across two operating system dialects. Then come plugins, networking, storage, logging. The source lists them as extensions, not as the core plot. The core plot remains declaration. Plugins are how a declared city grows neighborhoods. A different network driver, a different volume, a different place for logs to land, without rewriting the idea of a service. This is why YAML matters more than a screenshot of flags. Labels and constraints live in the file. A constraint can keep a database off a tiny node. A label can mark a host as the one with the fast disk. Swarm Scheduler reads those sentences when it assigns tasks. The plugins in the file are how a lightweight orchestrator still touches the real world of cables and disks, not just the world of ping. Look at the architecture the way a city map looks at power. At the top, 3 manager nodes. They are the ones who remember. Below them, worker nodes, where the actual workloads run. A node, in this language, is simply an individual Docker engine that has joined the swarm. Swarm itself is a mode, multiple Docker hosts running as one cluster. Managers are kept in odd numbers. 1 is acceptable when you are only testing, and availability is not a serious concern. In production, the usual choice is 3 or 5. Why odd? Because agreement is a vote, and a tie is a kind of silence. Workers, meanwhile, talk to one another with a gossip protocol. Not rumor in the human sense, but a quiet, constant exchange of who is alive, who is busy, who has room. The managers hold the distributed state. The workers hold the running work. Already you can feel the tension. A manager can assign work, but can it keep the whole system's story consistent? Why 3 managers or 5 and almost never 4? The source is brief and firm. We always have an odd number of manager nodes. Development or test may use 1 when availability is not a big concern. Production generally uses 3 or 5. The reason is quorum. Managers must agree on the cluster's story. An even council can split down the middle and freeze. An odd council can still produce a majority after 1 member goes dark. 1 manager is a single point of memory. 2 managers is a tie waiting to happen. 3 can lose 1 and continue. 5 can lose 2. Each extra manager is another machine that must stay honest and another vote in the room. This is why the architecture diagram shows 3 boxes in the state store region, not a decorative crowd. Those boxes are the difference between a cluster that forgets itself and a cluster that keeps scheduling after a manager dies. Workers can gossip all night. If the managers lose consensus, there is no authorized story to gossip about. There are only 2 kinds of character in this story, managers and workers. Start with the managers. These are the machines you speak to. They accept a command from a client and create service objects. They handle cluster management, maintaining the cluster state, scheduling services, serving the swarm mode HTTP API. They keep a consistent picture of the swarm and of the services running on it. They allocate IP addresses to tasks. They assign nodes to tasks. They check in on workers, personify them, and they are dispatchers with a long memory. They do not pick up the shovel. They decide which shovel exists, where it goes, and whether the hole still needs digging. If a manager forgets, the cluster does not merely slow down, it loses the plot. That is why production keeps more than 1, and why the number is odd. Consistency is not a luxury here. It is the only thing that makes 100 containers feel like 1 application. Workers are the other character. They are where containers actually run. A worker connects to the dispatcher, checks what has been assigned, and executes the task. Then it reports status. No speeches, no cluster-wide opinions. Strength and a blind spot. The strength is focus. Run this container, run this command, tell the truth about whether it is still breathing. The blind spot is authority. A worker does not invent the desired state. If the manager's story says 3 copies of a service, the worker does not argue for 4. That division is the whole politics of the swarm. Decision lives upstairs, labor lives downstairs. Gossip among workers keeps the neighborhood informed, but the census still belongs to the managers. When we later watch a node fail, remember this. The worker that dies was never the author of the plan. The plan can move. So what exactly gets scheduled? Not a vague container somewhere, a task. In Swarm, a task is the atomic unit of scheduling. In simpler terms, a task is a container plus the commands that run it. A small, schedulable fact. Manager nodes assign a task to a worker. The worker runs it and reports on its status. A task does not teleport into life. It progresses sequentially through states. Assigned, then prepared, then running, and so on. That sequence is the heartbeat you never see in a happy dashboard. Assigned means the decision has landed. Prepared means the node is making room. Image, network, the quiet chores. Running means the process is on stage. If you only watch the running box, you miss the politics that put it there. The example in the source is a service create that asks for 3 replicas of Redis. 3 replicas means 3 tasks, 3 chances to be assigned, prepared, and running. A task is running. Now demand doubles. What grows is not a feeling. It is the number of those atomic units. A single service is a soloist. Real applications are ensembles. Swarm stacks exist to define a number of services that make up a complete application in a specific environment. They are a convenient way to deploy multiple services that are linked to each other, without defining each one as a lonely object. A stack builds a more complex object. The source's picture is simple and exact. A few replicas of Nginx, an instance of MySQL, assembled in a Docker Compose file. Think of YAML here the way a conductor thinks of a score. Not one instrument's part, but the piece. It is similar, the source says, to a Kubernetes YAML that can include multiple deployments and the other resources an application might need. The idea is the same, even if the dialects differ. Stop babysitting containers as pets. Describe the living room and let the cluster place the furniture. The system is easy to describe. The next question is harder. Can a declaration survive a real deployment? Stay with health for a moment because the opening list treated it as a chore and it is actually the plot. Swarm keeps track of the health of containers. It restarts any container that has died or is deemed unhealthy. Those 2 sentences hide a loop. Observe, judge, act, observe again. A health check is not a compliment. It is a periodic question. Are you still the process I scheduled? If the answer is silence, the desired state is suddenly a lie. The managers still want n in running tasks. Reality has n-1. The scheduler's pride is to close that gap without a human in the room. Picture one of those 100 containers failing its check at 2 in the morning. Without orchestration, the failure waits for a person. With Swarm, the task is condemned and another is born. The application's name never leaves the service list. Only the inner cast changes. That is what ensure all containers are up on every system actually feels like. Not a guarantee written in law, a stubborn retry against entropy. The source names 2 cousins that operators confuse, adding updates to all the containers and performing a rolling update. The first is the wish. Every replica should eventually run the new world. The second is the choreography. You do not take the whole stage dark, swap the set, and hope the audience stays. You change one task, then another, while the service name remains on the marquee. Fixed deployments sit beside that idea. A fixed set of containers means the count and the shape are part of the declaration, not an accident of who happened to type Docker run last Tuesday. Rolling updates need that fixedness. If you do not know how many should exist, you cannot know when the roll is finished. Swarm's personality shows again. You declare. It converges. The update is not a festival of SSH sessions. It is another edit to desired state, walked out through assigned, prepared, running, while load balancing continues to sprinkle traffic on whoever is still healthy. The cost is patience. The gift is a show that never fully stops. Traffic is the other antagonist. A peak arrives. Users do not care which worker holds the lucky container. Swarm load balances traffic across multiple containers, and it allows services to be exposed with an ingress solution. Ingress here is a front door. Requests enter the Swarm and are handed to tasks that claim to be the service. Without that door, you would publish a single host IP and pray. With it, the service name becomes the addressable thing, and the tasks become interchangeable lungs. The source pairs this with balancing workloads across nodes when you schedule. Those are two different balances people mash together. Placement balance decides where tasks live, traffic balance decides where packets go. A cluster can be well placed and still poorly entered, or the reverse. Swarm's pitch is that it tries to do both. When we later hear the comparison table boast of auto load balancing, this is the scene it is pointing at. A city with a traffic department, not a stack of unmarked alleys. The tutorial begins the way a documentary should, not with mythology, but with a first switch. To create a new swarm, the syntax is docker swarm init, then advertise.adr, then the manager's address. Advertise.adr is the address other nodes will use to find this manager. The source walks two concrete tries. First, 192.168.99.100, a typical private lab address. If that does not work on your machine, use loopback, 127.0.0.1. After init, the swarm exists. The output includes a join instruction for other nodes. We will not linger on tokens. Tokens are keys, not ideas. The idea is this. One Docker host has just volunteered to remember. It has published a door. Everything that follows, workers, services, scale, depends on that first act of advertisement. A cluster that cannot be found cannot be joined. A manager that cannot be addressed cannot keep a city. The next command is almost humble. Docker info. You ask the engine to describe itself, and somewhere in that dump of facts, the swarm's state appears. This is not theater. It is the first proof that init did more than print a slogan. The host now knows it is a manager. It knows it is in swarm mode. It knows how many nodes it thinks exist. At this moment, usually one, itself. Documentary films love a wide shot of a factory. This is the equivalent. A status page. No containers yet, no workers yet. Just a memory that has been switched on. If Docker info still looks like a lonely daemon, the advertised address failed, or the mode never engaged. If it speaks of a swarm, the city has a mayor, even if the streets are empty. The empty street is the hook. A cluster of one is a cluster only in potential. Who else will join, and what happens if nobody does? Docker node ls is the census. It lists the nodes that belong to the swarm, and it marks a leader. On a brand new swarm, the list is short and a little proud. One host name, one engine. A star beside the leader, or a column that simply says leader. That word is doing more work than it looks. Among managers, leadership is the right to coordinate the state. Followers still remember. The leader conducts. Look carefully at what the table does not yet show. No workers, no down nodes, no availability drama. Just a single mind wearing both hats, manager and often worker as well, because a manager can also run tasks if you let it. The source's screenshot is a quiet document. The swarm exists and it knows who is in charge. The next sentence of the story is almost inevitable. A leader with no workers is a dispatcher shouting into an empty warehouse. Can we add hands without confusing the memory? To add a worker, you join. The command is docker swarm join, a token, and the manager's address on port 2377. The source prints a long token. We will not. Treat it as a sealed envelope. Anyone with that envelope can walk into the cluster. Anyone without it should not. After the join, the census changes. Docker node ls grows a second row. A worker appears, ready, unknown to yesterday's lonely info dump. This is the first time the architecture diagram stops being a drawing and becomes a room with two kinds of furniture. The manager still decides. The worker waits for the dispatcher. Gossip can begin, even if the conversation is still small. Notice what did not happen. You did not install a second orchestrator. You did not invent a new identity system from scratch. You pointed a Docker engine at another Docker engine and offered a token. Simplicity is the point, and already the security of that token is the cost hiding inside the point. A join is an act of trust. The cluster just got larger. It also got more ways to fail. Now the swarm has to earn its name. Deploy a service. The syntax is Docker service create, then replicas, then a name, then an image. Replicas is the desired count. How many tasks should exist if the world is healthy? The source's concrete line is almost playful. One replica. Name GFG. Image Alpine. Command ping docker.com. A tiny Linux userland, forever tapping a remote host just to stay alive and visible. Why ping? Because a service needs a process that does not exit. Orchestration is allergic to a container that finishes and walks away, unless you asked for that. Ping is a heartbeat you can see. After create, a service object exists in the manager's memory. A task is assigned, a worker prepares, then, if the picture is kind, the task is running. This is declared state in miniature. You did not SSH to a box and type Docker run. You told the cluster what should be true. One replica is not resilience. It is a proof of life. The crowd has not arrived yet. Docker Service LS is the program for the evening. It lists services by name, by mode, by replica count, by image. In the source, GFG appears. Replicas read 1 of 1 when the world matches the wish. That fraction is the whole philosophy of desired state, compressed into 2 numbers. The left number is what is running. The right number is what you asked for. Agreement is peace. Disagreement is a plot. A list with one service looks trivial. Do not be fooled. This table is how an operator learns whether the managers still believe the story. Later, when we scale, the right-hand number will jump first. The left-hand number will chase it. That chase is scheduling. That chase is assigned, prepared, running, happening in public. For now, the list is a still photograph. One named service, one desired replica, one running task if fortune holds. The hook writes itself. 1 of 1 is a single point of failure wearing a confident label. Demand doubles. In the tutorial, the double is modest, from 1 replica to 2, but the gesture is the same as a traffic spike on a public site. The command is Docker service scale, then the name, then equals 2. GFG equals 2. Watch what the managers do. They do not ask you which worker should wake up. They create another task. They assign it. A node prepares. A second Alpine begins to ping. When you list services again, the replica column should read 2 of 2. 2 tasks, 2 heartbeats. If those tasks land on different nodes, you have taken a first step toward surviving a single machine's death. If they land on the same node, you have only survived a single container's death. Swarm will try to balance, the source says, across the cluster. Balancing is not a guarantee written in stone for every tiny lab. It is the intention of the scheduler. Load balancing of traffic, health tracking, rescheduling after a node failure, those promises from the opening pages now have a physical object to hang on. 2 replicas, a crowd of 2. Small, but no longer a soloist. If scaling is this simple, what does the system give up? Every declared world should also know how to end. Docker service RM, then the name. GFG disappears from the manager's ledger. List services again, and the table is empty. The Alpine pings stop because the desired count is no longer 2 or 1. It is 0. Removal is not a crash, it is a decision. This is the last beat of the tutorial, and it is more philosophical than it looks. If create writes a wish, and scale edits a wish, remove erases the wish. The cluster is obedient in both directions. That obedience is what makes rolling updates possible later, and what makes a forgotten service dangerous if you never delete it. The source closes the walkthrough by saying you created a swarm, then nodes, then services, then learned to scale them and remove them. A complete loop. Birth, census, labor, growth, death. The fleet can now forget on purpose. The open question is what it still cannot notice on its own. You have heard of Kubernetes. The source treats it as the rival in the next room, another container orchestration tool, the one people name first at conferences. Swarm, in this telling, is an alternative, not a toy, an alternative with a different temperament. Instead of Docker daemons as the only local agent, Kubernetes would run kubelets on each node. Instead of Docker as the cluster brain, there would be a Kubernetes engine spanning the nodes. And then, the source says, the rest is almost the same. Same Docker containers, same applications, same hope that a cluster will outlive a machine. The conflict is not about whether containers exist. It is about how much machinery you accept in order to keep them. Swarm's personality is already on the table, included with Docker, declared in YAML, odd-numbered managers, gossiping workers, tasks as atoms, scale as a typed integer. Kubernetes arrives as the more famous cousin. The comparison table is where the documentary stops being a how-to and becomes a choice. Read the sources table as a set of claims, not as the laws of physics. First row, Docker Swarm supports auto load balancing. Kubernetes, the table says, does not have support for auto load balancing. That is the source's wording, and we will keep it labeled as such. In the story we have been telling, ingress and traffic spread across containers were part of Swarm's opening pitch. The table doubles down. Next row, and the temperament flips. Docker Swarm does not support auto-scaling. Manual scaling has to be configured. Kubernetes offers auto-scaling. Remember GFG equals 2. A human typed the 2. The managers obeyed. Nobody in that tutorial watched a CPU gauge and decided unbidden to become 3. That is the cost hiding inside simplicity. You get a short command, you remain the author of capacity. If the traffic spike happens at 3 in the morning, the source's swarm does not, by itself, rewrite the replica count. The rival's claimed gift is that it will. Already the documentary's central trait appears, a lighter hand or a more automatic one. Monitoring is the next fork. The source says Docker Swarm uses third-party tools for monitoring. Kubernetes has built-in monitoring. Health checks in Swarm still exist. We heard them on page 1. But the broader observatory, the dashboards, and the long memory of metrics is not presented as a built-in city service. You bring your own streetlights. Then installation. Swarm is simpler to install and set up. Kubernetes is much more complex to install and set up. This is the sentence that explains June 2016 and the switch inside Docker and the refusal to download a second universe. Complexity is not a moral failing. It is a tax. Teams pay it when the automatic gifts become mandatory. They refuse it when the fleet is still small enough to scale with a typed integer. Command lines follow the same split. For Swarm, the source says you do not have to learn a new command line tool. For Kubernetes, you must learn kubectl. The language of Docker service is the language you already speak. The language of kubectl is a second dialect. Dialects have power. They also have tuition. The last row is the verdict the table wants you to feel in your hands. Docker Swarm is lightweight and limited in functionality. Kubernetes has a higher learning curve and is more powerful. Limited is a hard word. It does not mean useless. It means the envelope is smaller. You have seen the envelope. Init, join, service create, scale, remove. Health, reschedule, ingress, YAML, stacks of Nginx and MySQL, odd numbers of managers, gossip, tasks that walk from assigned to prepared to running. That is not nothing. It is a complete answer to the 100-container panic, for a certain size of panic. Powerful is also a hard word. It means more knobs, more objects, more ways the desired state can be expressed, and more ways to get lost. The source does not crown a winner. It sets two philosophies on the table and lets the operator's night decide. Simple enough or too simple? The unresolved problem is not whether orchestration works, it is how much orchestration the future demands. Return to the wall of 100 containers. One of them still flickers. A machine still can vanish. Traffic still can double. But the story is no longer a person with a checklist. The fleet has a memory now. You can declare the desired world in a file. Managers keep that world consistent. Workers execute and report. Tasks move through states instead of appearing by magic. Stacks gather an application into one score. A swarm can be initialized, inspected, joined, served, scaled, and cleanly forgotten. When a node dies, the source's swarm will try to reschedule the work. When you ask for 2 instead of 1, the managers will try to make 2. What this knowledge made possible is repeatable deployment and a basic kind of resilience. the difference between a dead container and a dead application. What it did not settle is the last question the field is still chasing. When should simplicity yield to a more powerful, more complicated system? The switch is still there, inside Docker, waiting. Whether you should flip only that switch or walk into the larger machine depends on how loud the stampede has become.